Hello, my name is Shahriari, and this is a lecture in a series of lectures on elementary mathematics, basically topics that you might see in high school or possibly in middle school. The topic of this lecture is rational exponents and radicals. In this lecture, we will be talking about what does things like 2 to the 1/3, 3 to the 2/5, and so forth mean. In a previous lecture, I've talked about when the exponents are integers, whole numbers, things like 3, -5, and 0. 2 cubed means 2 times 2 times 2. What does 2 to the -5th mean? That means 1 over 2 to the 5th. 2 to the -5th, when that exponent is negative, does not give you a negative number. It gives you a fraction. 2 to the 0, in fact, anything to 0 other than 0 to the 0 is 1. These are all subject of a previous lecture. If you're not familiar with those, please watch that video first. Now, beyond the rational exponents, there are other things exponents could be, things like square root of 2. And for that, you need more fancy tools. We will talk about that briefly at the end. What does something like 2 to the square root of 2 or 2 to the pi mean? We will also talk about algebraic rules for exponents, which are basically the same as the ones for when the exponents are integers. And we will briefly mention exponential functions. When the exponent is a positive integer, a to the n means a times a times a n times. And a to the 0 is 1, as long as a is not 0. 0 to 0 is not defined. If n is a positive integer, minus n will be a negative integer, and a to the minus n, again, is not a negative number, it's a fraction. What fraction? 1 over a to the n. So you just write 1 over, and you write a to the positive exponent. These are, again, subject of the previous video. This last one makes sense if a is non-zero. If a is 0, then you will have a 0 in the denominator, and you can't have a fraction with a 0 in the denominator. These are all definitions. These are not things we prove or argue. Now, the rules, if a and b are integers, those are the exponents, and if the basis, the x, is non-zero, then x to the a times x to the b is x to the a plus b, x to the a to the b is x to the ab, xy to the a is x to the a, y to the a. The reason I want them to be non-zero, because some of these exponents could be negative, and therefore you might end up with a 0 in the denominator. Otherwise, these rules work no matter what x and y are and whatever integers a and b are. A couple of other rules that follows from those: x to the a times x to the b is x to the a plus b. When the bases are the same, you add the exponents. When the bases are the same and when you're dividing, you subtract the exponent. X to the a divided by x to the b is x to the a minus b. And x over y to the a is the same as x to the a over y to the a. We want to talk about rational exponents. What does apple to the 1/2 mean? By definition, that means square root of apple. And apple to the 1/3 means cube root of apple. If n is a positive integer, apple to the 1/n means, that's what we are defining it to mean, the nth root of apple. Apple has to be a non-negative real number. It can be 0, but it can't be negative. What does square root of apple mean? And this is for a non-negative apple. What does that mean? It's a number that when you multiply it by itself, you get apple. That's what's the definition of square root of something is. Square root of 2 is a number that if you multiply it by itself, you get 2. You might say, well, how do I know such a number exists? Actually, proving that these numbers exist will take some effort. But for square root of 2, for example, you can have a right triangle where the sides that are perpendicular to each other are size 1. Then the hypotenuse, but the Pythagorean theorem, is going to have the size square root of 2. That size, whatever it is, it's square root of 2. This number cannot be written as a fraction. You can write it in decimals, but that decimal representation does not end and does not repeat itself, does not have any patterns. So it's sort of a complicated number. The definition of square root of apple is that it's the number that if you square it, you get apple. Likewise, the nth root of apple is a number that if you take its nth power, you get apple as well. And these are only defined when apple is greater or equal to 0. So for example, 3 to the 1/2, that's square root of 3, and it's a number that's approximately 1.732. That's not exactly right, but it's approximately that. And you can see that if you take 1.732, square it, you will get something close to 3. And 5 to the 1/3 is cube root of 5, and that's approximately 1.71, which means that if you take 1.71 and cube it, you get a number close to 5. If you take cube root of 5 and cube it, you get exactly 5. But cube root of 5, if you write it in decimals, it's an unending decimal with no patterns, no repeating patterns. 9 to the 1/2, it's square root of 9, and that's exactly 3, because 3 squared is 9. 64 to the 1/6, what's that? 6th root of 64, which means a number that if you multiply it by itself, itself 6 times, you get 64, then that happens to be 2. What's 64 to the power minus 1/6? Again, minus means that you write a fraction. You write 1 over that same thing, but without the minus. So it's 1 over 64 to the 1/6. Then 64 to the 1/6 we just said is 2. So it's 1/2. So we talked about unit fractions, but what about other fractions? So apple to the 3/4, by definition, by what we have decided, it means the 4th root of apple cubed. So the 3 becomes a power, the 4 in the denominator becomes the 4th root. The 4th root of apple cubed is the same as the 4th root of apple cubed if apple is greater or equal to 0. Apple to the 4/3, as opposed to 3/4, is the cube root of apple to the 4th, or cube root of apple, all of it, to the 4th. In general, apple to m over m, if m and n are integers, is the nth root of apple to the m. And that's the same thing as nth root of apple raised to the power m. And this is for m and n positive integers. For example, 5 to the 2/3, what does that mean? That means cube root of 5 squared. So that's cube root of 25. That's a number that when you multiply it by itself 3 times, you get 25, and it's approximately 2.924. If you take 2.924 and raise it to the 3rd power, you will get something very close to 25. What's xy squared raised to the power 3/4? It's the 4th root of xy squared cubed. What's xy squared cubed? That's xy squared times itself 3 times. So it's the 4th root of xy squared times xy squared times xy squared. When you multiply those, the x's combine and the y's combine, so you get the 4th root of x cubed y to the 6th. What's 9 to the minus 3/2? Because of that minus, we first have to write that as 1 over 9 to the 3/2. 9 to the 3/2 means square root of 9 cubed. So it's 1 over square root of 9 cubed. What is that? It's a number that if you multiply it by itself, you get 9 times 9 times 9. Well, that's 3 times 3 times 3, because if you multiply that by itself, you get 9 times 9 times 9. So 9 to the minus 3/2 is another name for 1 over 27. Let me pause and talk about square root of x squared. If I ask you if x squared is 9, then what is x? Then you will tell me that there are 2 solutions. X is plus or minus 3. But if I ask you what's square root of 9, then what is the answer? Is the answer 3 or plus or minus 3? You might think that these 2 questions are the same, but they're not. When I say x squared equals 9, what is x? I'm asking you for all the solutions, and so you have to give me plus 3 and minus 3. But for square root of 9, we have defined that to be the positive root. Square root of 9 equals 3. It's not plus or minus 3. Now, why is that? This is a convention. This is what we have decided. And the reason for that is because we want the function y equals square root of x to be a well-defined function. For a function, when you plug something in, out should come just one number, not 2 numbers. When I plug in 9 into square root of x, I want to get one unique number, and that number is going to be 3. If I say plus or minus 3, there's ambiguity. If you plug in 9 into this function, what comes out? This is not really a function. If x squared equals 9, then what is x? X is not just square root of 9, because square root of 9 is just 3. You have to put a plus or minus in front of it. You have to say it's plus or minus square root of 9. This also tells us why when we do the quadratic formula, we've got a plus or minus there. Because when you're solving a quadratic equation, there is going to be 2 solutions. And there is a square root here. The square root isn't going to give you the 2 solutions. It's just going to give you one of them. And you need the plus or minus to make sure that you get both solutions. If someone asks you what's square root of x squared and you don't know what x is, then what is the answer? Is the answer x or plus or minus x? You might think that the answer can't be plus or minus x because I just went through all this song and dance to tell you that square root of 9 is not plus or minus 3, it's 3. So you might think maybe the answer is x. Well, actually, it's neither x nor plus or minus x. Why? Because we don't know what x is, and x could be negative, but we want square root of x squared to be positive. For example, if x was minus 2 squared is 4, and square root of 4 is 2. It's not minus 2. But if square root of x squared is x, and x was minus 2, then we would have to say square root of x squared is minus 2, and we don't want to do that. How do we get around that problem? We say that square root of x squared is absolute value of x. Absolute value of x means whatever x is, you just pick the positive. Because we want to assure that whatever comes out of the square root sign is positive, we need to put that absolute value there. Square root of apple squared is absolute value of apple. Let's talk about exponent rules. Apple and strawberry are a real number greater than 0, have the following rules, which are the same rules that were there for integer exponents. So apple to the a times apple to the b is apple to the a plus b. If the bases are the same and you're multiplying two exponents, then you add the exponents. This needs a proof, but I'm not going to go through those. Another familiar rule is apple to the a to the b is apple to the ab. So if you take one exponent and raise it to another, the powers multiply. And apple times strawberry raised to the power a is apple to the a, strawberry to the a. And just like with the integer exponents, we have two auxiliary rules. So apple to the a times apple to the b, that first rule was apple to the a plus b. Apple to the a divided by apple to the b is apple to the a minus b. If the bases are the same and you have two exponentials that you're dividing, you subtract the exponents. And likewise, apple divided by strawberry raised to the power a is apple to the a divided by strawberry to the a. How do you remember these rules? Just try them with some very simple example with integer exponents, and you will see what the rules are. For example, you might want to know how to multiply two exponentials, like x to the x, x to the b. What was the rule for that? Try something like 2 cubed times 2 to the fourth. What's 2 cubed? That's 2 times 2 times 2. 3 2's multiplied. That's what 2 cubed means. What about 2 to the fourth? 2 times 2 times 2 times 2. But when you multiply all of them together, you get 2 to the seventh, because there was 3 2's and 4 2's. That makes 7 2's. That should remind you that x to the a times x to the p is x to the a plus b. Now, this is a little bit misleading because we tried this for integer exponents, in fact, positive integer exponents, and then we are declaring that it works for everything, and that actually does need a proof. But the magic is that it does work. It does work for all kinds of exponents. After you try it for a simple example, you will remember the very general rule. Similarly, you might say, I want to know what an exponential raised to another one is. Try a simple one, 5 cubed squared. What is that? Well, what does 5 cubed squared mean? 5 cubed squared. That means that you have to multiply 5 cubed by itself. But what's 5 cubed? 5 cubed is 5 times 5 times 5. So how many 5s do I have? You can see that we had two sets of 3 5s, and 2 times 3 is 6. This should remind you that x to the a to the b is x to the ab. Finally, 3 times 5 squared. What is that? Well, 3 times 5 squared means 3 times 5 times itself. And 3 times 5 times 3 times 5 is the same as 2 3's multiplied, then multiply that by 2 5s. And so that's 3 squared times 5 squared. And that should remind you of the third rule. Xy to the a is x to the a, y to the a. If x and y are positive, we have defined x to the m over n to be the nth root of x to the m, or equivalently nth root of x raised to the power m. And we have 3 rules as our main rules. X to the a times x to the b, multiply two exponentials, the bases are the same, add the exponents. X to the a to the b is x to the ab, and xy to the a is x to the a, y to the a. For example, what does square root of 3 times cube root of 3 mean? Well, square root of 3 means 3 to the 1/2. Cube root of 3 means 3 to the 1/3. Now, when I write it like that, I see that I'm multiplying two exponentials and the bases are the same, so I add the exponents. And so I get 3 raised to the power 1/2 plus 1/3. 1/2 is 3/6. 1/3 is 2/6. I get 5/6. So this is 3 to the 5/6. And what does that mean? Well, that means the 6th root of 3 to the 5. So you multiply 3 by itself 5 times, then you find a number that if you multiply that by itself 6 times, you get 3 multiplied by itself 5 times. Can I simplify 6th root of 81? That means 81 raised to the 1/6. There's no one way you have to do this. In fact, the best thing to do is for you to stop the video, try and see how far you can get, and then compare with what I did. And you might have a better way of doing it than what I had. And 81, I'm going to write it as 3 to the 4th, because 3 times 3 times 3 times 3, 81. So 3 to the 4th is 81. So I have 3 to the 4th to 1/6. But now I have a power of a power. And so I can use my second rule and I can multiply 4 and 1/6. And 4/6, 4/6 is the same as 2/3. And so I have 3 to the 2/3. That means cube root of 3 squared, or cube root of 9. So 6th root of 81 is the same as cube root of 9. And if you think about it, that makes sense. Cube root of 9 is a number that if you multiply it by itself 3 times, you get 9. Well, if you take that number and multiply it by itself 6 times, well, of course, you're going to get 81. That same number that gives you cube root of 9 is also 6th root of 81. So you could have just thought about it and said that this is right. But this algebra helps us avoid thinking. In some ways, that's all it does. It makes into an algorithm. Sometimes the thinking through might be sort of hard. Cube root of 54, what is that? Well, 54 is 27 times 2. And 27 is 3 cubed. So 54 is 3 cubed times 2. So I'm really asking you what's cube root of 3 cubed times 2. And so that's 3 cubed times 2 to the 1/3. Now I can use my third rule. It's going to be the first one to the 1/3 times the second one to the 1/3. But the first one is 3 cubed to the 1/3. And I can use my second rule. I can say 3 cubed to the 1/3 is the same as 3 to, what's 3 times 1/3? 1. So 3 to the 1 times 2 to the 1/3. 3 to the 1, that's just 3. 2 to the 1/3 is cube root of 2. So I have 3 times cube root of 2. Do some more examples yourself. I've been insisting that the base has to be positive. Why did I? First of all, ideally, when we have x to the m over n or nth root of xm, those are the same thing, we want it to have a unique meaning. If I say square root of blah or cube root of whatever, I should be talking about one number so that when I tell you about that, you know what number I'm talking about. The mathematical way of saying that is that I want the function nth root of x to the m be a well-defined function. Functions, when you plug a number, ought should come just one number, not multiple choices. First of all, this radical notation, cube root of this, square root of that, is going to be unambiguous only for real numbers. If you include other things other than real numbers, things are not going to be unambiguous. People do use them sometimes for non-real numbers. We've got to be really careful because the rules don't quite work. For example, 2 cubed is 8. You believe that. But that's not the only thing that cubed is 8. Minus 1 plus square root of 3i cubed is also 8. Minus 1 minus square root of 3i cubed is also 8. These are complex numbers. I is a number that when you square it, you get minus 1. You might want to think of it as square root of minus 1. But there is a little bit of ambiguity because minus I also, when squared, gives you minus 1. You see that minus 1 plus square root of 3i and minus 1 minus square root of 3i, all cubed, give you 8. We have decided cube root 8 is the real number 2. Since there's only one real answer, we're limiting ourselves to real numbers, and therefore the answer is unambiguous. The answer is 2, and we don't have to really worry about it. With even exponents, like 2 squared is 4 and minus 2 squared is 4, we had decided that we're going to take the positive root. Now, we can do the same thing with some negative bases. For example, we could say cube root of minus 27 is minus 3, because that's the only real number that when cubed gives you 27. There are complex numbers, but as I said, we're eliminating those. But for example, square root of minus 4 is just not a real, there's no real number that satisfies that in the complex numbers. It could be 2i or minus 2i. But there's worse things than that. If you allow a negative base, then our rules do not work. For example, look at minus 4 squared to the 1/2. What is that? Minus 4 squared is 16, and 16 to the 1/2 is square root of 16, and that should be 4. On the other hand, if you use one of our rules and we multiply the exponents, 2 times 1/2 is 1, and minus 4 to 1 is minus 4. And so if the rules for exponent wanted to work, then we would get minus 4 equals 4. That does not work. We see that if we allow bases to be negative, then rules like x to the a to the b equal xab do not work. And that's why we want to limit ourselves to when the bases are positive real numbers. And the reason I don't want it to be 0 is because sometimes the exponent might be negative, and then that will end up giving you a 0 in the denominator, and that's a no-no as well. Let's say a couple of things about the exponential function. You can put x on one axis and 2 to the x on the other axis. When x is 0, what do we get? 2 to the 0, that's 1. When x is 1, what do we get? We get 2 to the 1, that's 2. When x is 2, we get 2 squared, that's 4. Then we get 8 for when x is 3, and 16 for when x is 4. As you see, this exponential growth goes up very fast. We can also extend this function for negative x. When x is negative 1, you get 1/2. When x is negative 2, you get 2 to the minus 2, so that's 1/4. And we now know that we can add other points here. For example, if x is 4/3, then 2 to the 4/3 is going to be cube root of 2 to the 4th. And that's another point that we could add. If we put all of those points in, all those rational points in, we will get the exponential function. 2 to the x is like this. 3 to the x basically looks the same way, except it goes up faster. It still goes through the same y-intercept. 3 to the 0 is also 1, but it goes up faster. Here, it might look like on the negative side that the curve hits the x-axis. It never does. It gets very close to the x-axis, but it's always positive. The x-axis is an asymptote for it. Now, when we draw this graph, we are making an assumption, which is that even if I put things for x that are not rational, things like square root of 2, for example, that they have a meaning also. And in fact, if this graph is right, I can go up to the graph and figure out what that 2 to the square root of 2 means. That needs actually a lot more work to make sense out of it. Instead of 2 to the x, we could also look at 2 to the minus x. 2 to the minus x is 1 over 2 to the x. So what happens is that when you plug in 2 here, you get 2 to the minus 2, which is 1/4. But when you plug in minus 2, you get 4. If instead of x, you put minus 2, 2 to the minus 2 becomes 2 squared, becomes 4. And so this is exponential decay. When you have exponential functions with negative exponents, you get exponential decay. So finally, let's talk about when the exponent is not rational. What does 2 to the square root of 2 mean? If you just want to think about it in terms of exponents, it's very hard to come up with like it's 2 multiplied by itself. What? That doesn't quite make sense. And the answer is actually not so straightforward. There's 2 different ways of giving meaning to 2 square root of 2 so that in the graph, it all works out well. And the rules for exponents works well. One way to do it is to say, well, square root of 2 is approximately 1.4142, and that goes on forever. So that means that if I start with 1, then 1.4, then 1.41, 1.414, and so on, this sequence converges to square root of 2. It gets closer and closer to square root of 2 and doesn't go away. So I'm using the concept of convergence and limits to talk about this. And so if that's the case, then we can notice that these actual 1 and 1.4 and 1.41 and so are rational numbers. Our ratio of integers. Square root of 2 is not, but these guys that are approaching it are. This is a sequence of rational numbers that converges to this irrational number, square root of 2. And the reason they are is because 1 is 1, but 1.4 is the same as 14/10. 1.41 is 141/100, and 1.414 is 1,414 over 1,000, and so on. So these are rational numbers that converge to square root of 2, and we can raise 2 to the power of these. And so we could say that 2 to the square root of 2 is the limit of 2 to the 1, which is 2, but then 2 to the 14/10, which means what? The 10th root of 2 to the 14th, and then 2 to the 141/100, which means that 100th root of 2 to the 141, and so on. This is a very complicated sequence that should converge to 2 to the square root of 2. We, of course, have to prove that it does converge, that there is a limit, that this does approach an actual number, and you can do that. Of course, this is not very practical in terms of doing things with 2 square root of 2 or 2 to the x in general. The much better way is given to you by calculus. This is actually one of the powers of calculus that allows us to define exponents for irrational exponents. And I'm not going to go into it in this video, but the way you do that is you first define logs. In the usual way you learn in high school, you first learn exponents and then you do logs. In fact, in my next video, we're going to talk logs using exponents. But the real way, the mathematician's way of doing this is to start with logs. Actually, to start with something called the natural log. And you use integrals to define that. Then from logs, you get exponents as inverse functions of logs. So you go the other way, and then you can prove all properties of exponents very clearly. This is the end of this lecture. Subscribe and like my videos if you would like to see more math videos on your feed. See you next video.